Good morning, my YouTube viewers. It's Crystal here. I wanted to make you another video, and this video that I'm making is going to be how to make a poisson distribution and test it using Python in Excel. And I want you to look at the screen right now because this is what it's supposed to look like. But I'm using Python that's on the cloud, and obviously I don't have a lot of money, so I'm not paying to get the fast Python. And since I'm not paying to get the fast Python, this Python is really slow, and it takes a long time to get it to work. And since it's working now and it looks good now, if you just look on the screen, you'll see what it's supposed to look like. So I've made 3 Poisson images. You can see 1, 2, 3. You can see that a Poisson image is right skewed. And then what I did was I checked the means of those 3 Poisson images. And so the means are going to be very similar. And the reason why the means are very similar is because I just used the same data for each Poisson image. But the thing is, it's like if you wanted to, you can change the data and make it different. And then if you change the data and make it different, then what's going to happen is your test is going to come out different as well. But just for this example, I made the 3 Poissons that have the same parameters, which is why they have very similar means. And you can see a Poisson distribution. You can see it's slightly right skewed. So I'm going to show you the code. First thing I'll do is I'll show you the means for the 3 Poisson distributions, because that's an easy piece of Python code to look at. So you've got mean 1 equals Poisson 1 dot mean, and then you have to say mean 1. So it's similar to a Jupyter notebook. If you've ever used a Jupyter notebook, then you'll know that the last command, the last bit of code is what it displays. So you have to say mean 1, mean 2, mean 3 as the last bit of code. So that's your mean. That's the easiest piece of code. Now we're going to do the Poisson image, where you don't have to do an image. You don't have to, but I wanted to do an image. So lambda value 1, comma size 1 equals 5, 1000. And then we generate the Poisson distribution. Poisson 1 equals np.random.poisson lambda value 1 size 1. And then we use matplotlib to create an image. So of what this Poisson distribution. Now the thing that you need to keep in mind, and I'll show you a little bit later, is all of the libraries. You have to import them. You have to import all of the libraries, and you have to import all of the libraries in the first page, the first spreadsheet of this workbook, because what Python does and what Excel does is they know to look in the first page of the worksheet to find the libraries. And so that's what I've done. I've imported all the libraries, and I will show you that as soon as I show you the code. Now the problem that we're going to get into is because it's so slow that if I decided that I wanted to change any of the parameters, like to make lambda value 1, 6 instead of lambda value 1, 5, it would take forever for it to work because I would get a busy signal, and then I would get a calc signal, and then I might even get a Python signal, and all of those are like error messages. And then finally, after a long time, I would get the result because this is a slow process. That is one of the disadvantages of using Python in Excel. And I don't know if it makes it slower because I like to have lots of pages in my workbooks. Now, possibly if I made one Excel file for every distribution, then there's the possibility, I think, that it would be faster because it would not have so many commands that it would have to process. But that's why I like using Excel, is because I can do every distribution on a different sheet, and then I can just save it as statistics with Python, or I can save it as Python distributions or something like that. So this tool has advantages and disadvantages. The advantages that I can put a separate program on every sheet, and then let's say, and then I just have it all on one spreadsheet or worksheet, rather than having to go around looking for it, because that's what I have in my Jupyter notebooks in Google Drive. So in Google Drive, I have one program for everything, and then you have to go through looking for it. So I've been programming in Python for like 4 years now, and so I've got 4 years worth of programs I have to go looking for. So that's why programming in Python and Excel has its positive points and its negative points. So now we're going to talk about the Poisson rate test distribution session 1 and session 2. And this is the code for that. Poisson rate test. It says sample data, observed rate 1 equals lambda value 1. That's from your Poisson. Observed rate 2 is lambda value 2. That's from Poisson 2. N1 equals size 1. N2 equals size 2. And then calculate the pooled rate. Pooled rate equals observed rate times N1 plus observed rate times N2 over N1 plus N2. Now we calculate the z-score, or the test statistic. Z equals observed rate 1 minus observed rate 2 over the square root of pooled rate times 1 over N1 plus 1 over N2. And now we calculate the p-value. P-value equals 2 times norm.cdf brackets ABS negative ABS Z. So we're using, in this particular test, we're using the cumulative distribution function, because when you're dealing with statistics, you've got a probability distribution function, which is your probability, and then you've got your cumulative distribution function, which is accumulation. And this is the formula that is on the internet, so I have to take that as being the formula that they want, and then you check your p-value. So z is 0 and p-value is 1. Now that's just what it came out with. So, and that's because the Poissons are so close. I also did actually find like a tiny little typographical error that I could change, but I don't dare do it, because if I change this tiny little typographical error, then it's going to just mess up the whole page and I won't be able to continue with the video. So now what we're going to do is we're going to cover Cochrane's Q test, and that's a new test. And so 1 is for success and 0 is for failure. Result equals Cochrane's Q, and then it's going to be poisson 1, poisson 2, and poisson 3. And then we're going to print off the result statistic and the result value. So the result p-value. So the result statistic is 995.7974, and the p-value is 0.522. So the thing is the p-value is going to be higher than the alpha. So we can say here the alpha is going to be 0.05, which is typical, and that means it's going to accept the null hypothesis. So the null hypothesis is that the distributions are the same. And of course we know they're the same because we got the means. You can see the means. But I could do it. What I could do is I could change it, and then that would change the change your means. And then if it changes your means, then it's going to change your z statistic and your test value as well. But before I go any further, I said that I was going to show you where the first page has to be import libraries. So I've got here, I've got import, and you even have to import, even though Excel says that these libraries are already imported as a matter of course. I'll go ahead and import them anyway, because I can tell you math is an inbuilt library in Python, and the program didn't work until I imported math. And then so I've got these libraries imported. I've got all of my SciPy libraries imported and the functions imported with that. And then I've got my stats models libraries imported. So SciPy is Python scientific library, and stats models is Python's statistics library. But SciPy does have statistics functions in it, and I'll tell you honestly, I like SciPy better than stats models. The documentation on stats models isn't that good, in my opinion, and so you have to go around looking for code. And then so the way that they did it with the Cochrane's Q was they made a data frame, and they put a data frame in the function, but I didn't like that. And so what I did was, rather than put a data frame in there, I put the 3 poissons inside brackets to let them know that it was one bit of information. So I've showed you everything. You can experiment on your own if you decide to do your own Poisson's distribution and test it. You can experiment on your own, because I'm just worried that if I do anything, then it's going to mess up all the code. But you can change the parameters of the Poisson distribution, and if you change the parameters of the Poisson distribution, then that should change your means, and it should also change the tests that were performed. But it does take a long time. I will say this, like last night I was working on it, and I don't know if lots of people were working on Python and Excel last night, but last night it just took absolutely forever to do it. And then so I'm a little bit scared. I'm a little bit scared to do anything. So I'm going to go ahead and close this video, because I've talked to you about the distribution, the means, and the 2 tests that we use to test it. And I've showed you where you can change the parameters yourself. You can change the lambda value and to be another number. And if you change the lambda value to be another number, then that's going to change your means, and then that's also going to change the result of the test. So that's something that you can do on your own. So thank you so much for watching my video. If you like my video, please like and subscribe, and I will be making another video for you in the very near future.